Hello and welcome to this tutorial video. So this video is part of the Introduction to Artificial Intelligence and Machine Learning for Engineer class. So what we are going to see today is to see an illustration of how we can implement a search algorithm to solve a logic problem using a computer. So here in this case, we are going to take an example of a puzzle game. And we are going to see how we can have a computer solve this puzzle game by thinking like a computer and not by thinking like a human. So if you are a human and you are trying to solve a puzzle game, usually you will use your intuition or you will try to find some logics to solve these problems. But for a computer, the computer doesn't have the level of intuition that humans have. So they have to solve games by using some kind of algorithm, by using some kind of instruction, some list, a given recipe, following different instruction one after the other. So this is something that can be achieved with the AI algorithm that we saw during the previous lecture. And here what we are going to see is an example of such problem and how to implement a search algorithm in Matlab in order to solve this logic problem. So here the problem that we are going to solve is the case of a sliding puzzle. So imagine that you have a 3x3 grid. So 3x3 squares, a grid of 3x3 squares. And one of those squares is empty and the other squares are filled with some tiles. And those tiles can slide vertically or horizontally. So this is like a sliding puzzle game that you may have encountered in the past. And the goal here is that initially those slides are randomly distributed. They are just randomly placed. And we want to slide those different tiles in a smart way so that so as to achieve a given target sequence. So here the example that we are going to take is an example where you have so a 3x3 grid where each tile has a given number, and then you have one empty space where you can either slide up or slide down or slide left or slide right some of the tiles, and each of the other tiles has a given number. So since there is 9 squares, so you have 8 tiles that are numbered as 1, 2, 3, 4, 5, 6, 7, 8, and then the last remaining slide is the last remaining square is just empty, and this is the space that is used to slide the other tiles. So we are going to see how to solve this puzzle, this sliding puzzle, by coding a search algorithm in Matlab. And for this, we are going to see an example of implementing a breadth-first search algorithm, which is an algorithm that is not very efficient, but that is guaranteed to find the most optimal sequence of action that allows you to reach the goal, starting from the initial state to reach the final state. So let's first illustrate a little bit like the problem that we are trying to solve. So here, again, so we are going to focus on some 3x3 puzzle, sliding puzzle game, where in this case the state of the system at a given time will correspond to the position of each of the 8 tiles. So the way we are going to represent this is that we are going to represent it as a matrix, and this matrix is going to contains the position of the tiles. So let's first generate an initial configuration for the sliding puzzle. So let's generate an initial configuration. When I say configuration, I mean the actual positions of the slides of the tiles for the sliding puzzle. So we are going to encode this configuration as a matrix. So we are going to call I the initial state. So the initial state will be a 3x3 matrix So I'm going to take a random matrix. So for example, so I need, so this is going to be a 3 by 3 matrix, and I'm going to place randomly inside this matrix all the integers between 1 to 8 and 1, 0, which will correspond to the empty square within this sliding game. So let's take an example. For example, let's define a matrix for which the first row would be 4, 1, 2. The second row, so I need to make sure I don't use the same integer twice because each tile is going to have a different number. And so the last one, so for example, will look like this. Okay, so let's take this. So let's see what this matrix look like. Okay, so here you see the actual puzzle game. So here, like each of those integers, think about them as a tile that you can slide left, right, up or down. But you can only slide this tile if there is an empty space to slide this tile. So here the 0 corresponds to the empty space. So this 0 is actually an empty space, which means that here the only 2 actions that I can take starting from this configuration would be to take the 7 and slide it down, or to take the 8 and slide it left. Those are the only 2 moves that I can take. I cannot take any diagonal move. I cannot take the 5 and slide it diagonally to the 0. That would not be an allowable move. And I cannot do anything else. I cannot move the 4 because it's already surrounded by 2 other tiles, the 7 and the 1. And so here we have 8 tiles. Each of them is denoted by a different integer. And again, this 0 is not actually a tile, it's just an empty space that allows us to move the 7 or move the 8. Okay, so this is the initial random state of the system. And I'm going to define the goal, the goal that I want to achieve. And the goal that I want to achieve here is to reach a state where all the integers are perfectly ordered in terms of increasing number. So I want to reach a state where the puzzle will feature the tiles as being 1, 2, 3, 4, 5, 6, and 7, 8. And then I want the 0 to be at the last position. I want the last position to be the empty square. So this is the goal state that I want to reach. I want, starting from this configuration here, this configuration I want to move I want to slide the tiles one by one in order to reach this goal configuration where all the tiles have been moved in order to reach this very ordered configuration with tile 1, 2, 3, 4, 5, 6, 7, 8. And the 0 is where you would actually have the empty space. Okay, so this is going to be the initial state and the goal state. And I want to see what is the optimal sequence of actions. What is the minimum number of times that I have to I have to slide those tiles in order to go from the initial state to the goal state for this problem. Okay, so we are going to implement this using Matlab, and we are going to implement a breadth first algorithm, so a breadth first search algorithm. So in this case, this breadth first search algorithm probably would actually not be the best choice to solve this problem because it's not a very efficient algorithm, and the frontiers can become very, very large because you have a high number of possible actions that you can do. So that probably would be a pretty inefficient algorithm. So we can find probably some smarter algorithm to solve this problem. But for the sake of this example, I'm just gonna use this algorithm because it's easier to understand. And hopefully that's still going to allow us to solve this problem without too much computing time. So let's see the different steps that I will have to do. So again, this matrix here is going to be the initial state, and I want to see what is the minimum number of actions that I need to take in order to reach the goal state, in order to transform this matrix I into this matrix J. So the first thing in order to achieve this is that, so I will implement the breadth first search algorithm. And so for this, you need to have watched the previous video, the previous lecture on the introduction to the search algorithm, to the uninformed search algorithm, introducing the breadth first search algorithm. So I will use some concepts that have been introduced in this lecture. So here we are going to use an uninformed search, which means that we are going to just explore the game tree. We are going to explore all the possible states, but without having some information as to whether we are going into the right direction or not, as we would have in an informed search algorithm. So here we are just going to use this uninformed search algorithm using the breadth first search algorithm, which again is probably not the best choice here, but it's still going to give us at the end the optimal solution to this problem, the minimum sequence of action, the minimum number of actions that are needed in order to solve this problem. Okay, so the first thing in this case, remember that in a search algorithm, what matters is how do you explore the frontiers of all the states. So here, the basic idea of this search algorithm is that we are going to start from a given state, which is going to be state I. We are going to expand this state. So we're going to find all the other possible states that can be reached by taking a given action from state I. Here in this case, if we start from state I, there is only two possible actions that you can have, which is to move down, to slide down 7, or to take 8 and to slide it towards the left. Those are the only two possible actions. So that's going to give you two successors, two possible states. Starting from the parent state I, you will create two children state, and this is, we are going to put those two states in the frontier. And then we are going to start exploring the elements in the frontiers one by one. And every time we explore one new state, we are going to expand this state. So we are going to see what are all the other possible states that can be reached by taking some actions from these states. And every time we find some new states, we will add them to the frontier. And this frontier is going to be a queue that contains all the possible states that we have found, and we will explore them and expand them one by one until we find the goal state, until we find that we have reached a configuration that is equal to the goal states. Okay, so let's start by initializing the frontier. So here, the frontier, we are going to define it as an array. Like this, with some bracket like this. It's gonna be a list of all the possible states that we have in stock and that we have not visited and expanded yet. So this is the queue of all the states that you have found during your search, but that you have not explored yet. So this is like some kind of queuing system where every time we find the possible states, we put it in the frontier. And so that we can keep the memory of the states and we can remember to explore potentially this state later on. So we are going to also start with the first possible state, the starting state. So here what we are going to do is to say that we are going to initialize this algorithm by initializing what is the first state that is going to be visited. And so we are going to call this the parent state. So I'm going to call it P. And so the first parent state that we are going to consider is just the initial state I. So this is going to be the the first state that is going to be visited during this search. And so then we are going to start the search from this point. So we're going to start the breadth first search. Okay, so this search is going to continue until the state that we are exploring become equal to the goal state. This is when we know that the algorithm has become successful. This is when the state that we have found is actually the same as the goal states. This is when we have moved all those tiles in such a way that they are now ordered in terms of increasing integer number. So this is when we know that the algorithm has actually found the solution to this logic problem. So it has found the goal state. So we are going to continue this search until we find that the state, the parent state that we are exploring, becomes equal to the goal states. So for this, we're just going to compare the parent matrix P that we are going to be exploring and to compare it to the goal state. And if P becomes equal to the goal state G, then we are going to stop the search. So one way to do this is to say that I'm going to check is P equal to G. So this condition here is going to tell me, is the matrix P equal to G? And I want to continue the loop, continue the search until this matrix P becomes equal to the matrix G. So I want this search to continue as long as those two matrices are not equal to each other. So I want this loop to continue until those two matrices are not the same as each other. So I'm going to continue this search while P is not equal to G. If P is not equal to G, then I know that I haven't found the goal state yet, so I need to continue the search. Okay, so let's continue from there. So the one thing that will be needed first is, once we have a parent state P, we will need to expand these states. We will need to find what are all the other possible states that can be reached starting from the state P. And so for this, I need to know what are the tiles that I can move. So I need to know what are the allowable moves that I can do. So for this, I need to know where is the empty space, where is the state, where is the position of the space that is labeled as 0 here, which is actually the empty space where I can move the other tiles. So I need to know where is this empty space. So this is the first thing, is where is the empty space. I need to know the position x and y of this state. So the way we are going to do this is to say I'm going to store as x and y this is going to be the coordinates of the empty space. So, and I'm going to determine this empty space by finding where is P equal to 0. So P is a matrix, and I'm going to find where is P equal to 0, and based on this is going to give me the coordinate of where P is equal to 0. So for example, let's take an example here. So I have this is my starting state, the starting configuration. So if I look at where P equal 0, so sorry, I equals 0. So I equals 0 is gonna define a new matrix where every time the element of this matrix is actually equal to 0, it's going to say that this element is indeed equal to 0. So if I want to find the position of where the element 0 is located, in this case, the element 0 is located in the first row and the third row, first column. So if I want to find the position, I can define x and y, the position, and to say I want to find where the matrix I, where are the elements that are equal to 0. And if I do this, it's going to tell me that y equal 3, x equal 3 and y equal 1, which means that the element 0, which corresponds to the empty space, is located on the first line, the third row, and the first column. So it's going to tell me that it's located at the position x equal 3, y equal 1. So third row and first column. So I'm going to use this to here define that the position x and y of the empty space, and this is going to help me to understand what are the tiles that can be moved in this game. So now what we're going to do is, now that we know where is the empty space, now we can figure out what are the allowable actions that can be taken. We can figure out what are all the possible moves that we can perform, what are the tiles that can be moved in this puzzle. So here there is 4 possible moves that you can have. Is if you have an empty space, you can either move one slide to the right, one slide to the left, one slide down, or one slide up. And so you have those 4 possible actions to move the tiles, but some of those actions are possible and some others are not possible. So we need to figure out what are the possible actions that can be performed depending on the position of the empty space that you can have. So here what we are going to do is to figure out all the possible actions that can be performed, and based on those actions we can figure out what are the new states that can be achieved from this parent state. So this is going to give us all the children, all the successors of this state, and this is going to correspond into the expanding the state. So here we are visiting the state P, and we are going to expand the parent state P. So here that we will have a big block of code which will correspond to expanding, starting from this parent state, what are all the possible other states that can be reached, what are all the possible action that I can take. So the first thing that I can do is, if there is an empty space, I can move a tile up. But in this case, for example, if you take the initial state that is here, since the empty space is at the bottom, there is nothing that I can move up. In this case, there is no tile that I can move up into this empty space because there is nothing below the empty space 0. So in this case, I would not be able to achieve this. So I need to find what is the condition according to which I can move a tile up. And this condition is I can move something up if the empty space is not on the third row. If the empty space is either on the first or on the second row, then it means that I will be able to move a tile up. So here the condition for me to be able to move a tile up is that, actually I'm going to start by the other case, moving a tile down. So in this case, I want to check, can I move a tile down? So in this case, I can move a tile down. I can take the tile number 7 and slide it down towards the empty space. But I would not be able to do this if the empty space was on the top. If the empty space was on the top, then there would be no tile that is on top of this empty space that I could move down. So this, the action of moving a tile down can only be taken if the empty space is either on the row number 2 or on the row number 3. That is to say, if the row position X of the empty space is strictly larger than 1. So if it's either 2 or 3, then I can move a tile down. So I'm going to have this condition to say that I can only move a tile down if the empty space is larger, strictly larger than 1. So then I need now to determine what is going to be the child state that I will get if I move a tile down. So for this, the child state will be mostly similar to the parent state. So because I can only move one tile at a time. So the only difference between the parent state P and the child state C will be only one tile that is going to be moved, that is going to be translated from one position to a neighboring position. So since those two states are very similar, I'm going to start first by taking the state P, the parent state, and to copying it into the child states, because most of the position of the tiles will be the same, and I will just need to change the two states that corresponds to the slide that I'm moving from one position towards the empty space. So here, if I'm moving a tile down, so I need to move the tile that was on top of the empty space, just on top of the empty space, and move it down towards the empty space. So the tile that was on top of the empty space, it was located at the position x minus 1. So x minus 1 corresponds to the previous line, the previous row before the empty space. So this is the line that is just on top of the line where the empty space is located, and it's at the same column y. So again, if the empty space is located at xy, the tile that I can move down towards this empty space is located at x minus 1y, which is the position of the tile that is exactly on top, at the same column y, but at the line x minus 1. And so this is the tile that I can move, and I'm going to take this tile and move it down and put it at the position of the empty space xy. So I'm going to, in the child state, I'm going to take the tile that is on top and put it at the position xy, which is the position of the empty space in the new child state that I'm creating here. So if I do that, it means that I'm moving the tile that is on top of the empty space, and I'm moving this tile down, which means that now the former position of the tile is now going to be empty. So this is where the new empty space will be located. So I need now to say that in the child state, the former position of the tile, which is located at x minus 1y, this tile is now going to be empty. So this the integer in this tile is now going to be 0. So if I do that, it means that now I have created a child state, which is very similar to the parent state, but just I have switched two tiles. I have taken one tile, move it down, moving this tile down, which means that the former position of the tile is now empty. So it's now occupied by a 0 integer. And so here it means that I have created a new state, C, which is one child of the parent states. So I need now to say that I'm going to add C to the frontier. So C is a part of the successors of the state P. So I need to add this new state that I have found to the frontier. So here, initially my frontier was an array that is initially void. but as this algorithm runs, this frontier is going to be start to be populated by more and more states that needs to be visited. So here I'm going to, since I have found a new child state, I need to add this state to the last position of the frontier. I don't want to replace anything that was already in the frontier. I just want to append the frontier, to keep the frontier and to add one extra element to the frontier, to add one extra element to the queue of all the possible states that needs to be visited. So one way that I can achieve this is to say that I'm going to take the frontier initially as a given number of elements, and I'm going to say that, so end means that this is the position of the last element of the existing frontier, and I'm going to say that I'm going to add a new element that is going to be located at the position n+1, and in this at this location, this is where I will put the new state C, the new matrix C that I have found. So here it means that I'm expanding the frontier. The frontier used to have n states inside this frontier. Now I am adding at the position n+1. I'm expanding the frontier in order to add this new state C, this new child state that I have found. So this is the first possible action that I can take. So there is 4 other possible actions, but they are going to be pretty similar, so I can go a little bit faster. So the second thing that I can do is now to move a tile up. So moving a tile up means that you have a given empty space somewhere, and that you have the tile that is located just below the empty space, and that you can slide this tile up in order to move this slide towards the empty space. Again, for example, in this case, if you take the initial state I, you would not be able to do this because there is nothing below the empty space. So you could not take any tile and move this tile up in order to fill this empty space. So the only case for which you would be able to do that is if the empty space is located either on row 0 or on row 1, or on row 2. If the empty space is located on row 3, then you cannot move up any tile towards this empty space. So the condition in order to do this is that the position of the empty space needs to be strictly smaller than 3. This is the only condition where you can move up a tile to this empty space. Then the rest is going to be pretty similar. I'm going to take my parent state and copy it into the child state because the child is going to be very similar to the parent. Now I'm going to say that I'm going to take the tile that was located below the empty space. So this tile is now going to be located at x+1 y. This is the position that is just below on the same column, but just at the next line, just below the empty space. And I'm going to take the tile that is in the parent state is located at x+1 y and put it in the child at the location of the empty space. And now I'm going to say that in the child, because I have moved up the tile, the initial position of this tile, which was initially at x+1 y, is now empty. So it's going to be filled with a 0. And same thing, I'm going to say that my frontier is going to be expanded. I'm going to append one new element to the frontier. And I'm going to put this new child state that I have found and put it inside the frontier. So you can notice here that I have a first condition here to check if I can move a tile down, or a second condition here if I can move a tile up. But here, those are two independent conditions. This is not a if something, then something else, or else something else, because it's possible that if the void is in the middle on the line number 2, then I can take a tile and move it down, or I can take a tile and moving up. So potentially those two action might be both possibles. So it's not like one or the other, like potentially all those two actions, including the one that are going to follow, they can all be possible potentially. So we need to make sure that we don't miss any child state. So we need to make sure we fully expand this state P and find all the possible children states, all the successors of the state P. So we have tried to move a slide down, move a tile down, or move a tile up. So now I'm going to try to move a tile right. So this is going to be the same spirit. So I'm going to move a tile right this time. So the condition for being able to move a tile right is that I need to make sure that I'm able to do this. For example, here, if you take the initial state, what I can do is to take 8 and move it towards the left. But I cannot move any tile toward the right because there is nothing that is on the left of the empty space. So here I would not be able to move any tile towards the right. And this is because the position of the empty space is on the first column. So it's y is equal to 1. It's on the first column, which means that in order to be able to move a tile towards the right, I need to make sure that the position of the empty space is either 2 or 3. Its column should be 2 or 3. So here now the condition is not regarding x, it's regarding y. So I need to make sure that y is strictly larger than 1. It's either 2 or 3. That's the condition to make sure that I can move a tile towards the right. So in this case, I'm going to do the same thing. This time I need to find what is the tile that I'm moving. So the tile that I'm moving is the tile that is on the left of the empty space. So the tile that is on the left of the empty space, it's on the same line x, but it's on the previous column x, y minus 1. So I'm taking this tile, I'm moving it to the position that used to be empty. And now I need to say that the initial position of this tile is now going to be the empty position in the child, and I'm adding this child to the front here. Okay, and the last possible action is to move a tile left. So now the condition in order to move a tile left is to make sure that there is actually a tile that is on the right of the empty space, and this is only possible if the void is not on the last column, number 3. So I'm going to do exactly the same thing. In this case now, what I'm going to do is take the tile that is located on the right of the empty space, moving it to the empty space and saying that the initial position of the tile is now going to be empty. So here, if you look at this, it's pretty obvious why it's indeed important to check that the empty space is located at a column that is lower than 3, because if it was 3, if the empty space was located on the third column, then y would be equal to 3, and here we would be checking what is the value of the tile at the column 4, but there is nothing at the column 4, so there is no tile at the column 4. Column 4 doesn't exist, so this is why we need to make sure that this the empty space is not located on the last column of the sliding puzzle. Okay, so what we have done here is we have listed all the 4 possible actions that can be accomplished. For each of those 4 actions, we have checked if they are allowable or forbidden by checking, depending on where the void is, what are the actions that can actually be taken and which one are actually forbidden. And whenever those moves are allowable, whenever they give birth to a new state, a new child state that is an allowable state, then we have added this state to the front here, to the list of all the successors that we need in the future to explore and to expand. So now that we have this, the expanded, added some new element to these frontiers, we are going to move to the next state. Since we know that this initial state was not the goal state, now we need to move to one of those 4 states that was added to the frontier. And so this is where the breadth first algorithm is actually starting. So far, it was just the basic, like the basics of any, of virtually any search algorithm. You just expand the nodes and you find what are the possible actions that you can take. This is any search algorithm, or almost every search algorithm will need to do that. The difference between the search algorithm is now that you have a frontier, this frontier here potentially contains up to 4 elements, 4 possible states that you can visit by sliding the tiles up, down, right, or left. And now you need to choose which one of those 4 states are you actually going to explore next and expand. And in the breadth first algorithm, the way this algorithm works, again, if you haven't seen the video, the previous lecture on this, you would need to watch it. But the basic idea of the breadth first algorithm is that you will always explore the first element in the frontier, which corresponds to the oldest state that you have added to the frontier. Every time you add some new states to the frontier, you add them on the right at the end of the frontier. But when it comes to exploring the new states, you will always explore in priority the oldest states that you have found. So the very first states, the one that are located on the left of the frontier, on the first position of the frontiers. You are going to look at those very first states, the one that you found as early as possible during this search, and you are going to look at them, and after looking at them, you will remove them from the frontier, but you will always start with the oldest states that you have found, not the newest one that you just found. You will always focus on the first states, and that's why the breadth first search algorithm is always going to give you the most optimal sequence of action at the end, despite the fact that it's very inefficient, because it always focuses on the very first states that you have found. So now we are going to decide what is the new states that we are going to visit. So we are going to visit a new child state in the frontier. And again, here in this case, we are just going to say that, so we have the given frontier F. This is an array that contains all the possible states that needs to be visited. And here, for the breadth first search, I'm going to say that I'm going to just take the first element of this frontier, and this is going to give me the new parent state that I want to visit. So in this case, this is this is where the breadth first algorithm, this is really what the core of this algorithm is I'm always going to focus on the most ancient states, which is located at the first position of the frontier. So yes, so this is what I'm going to do. So I take the first element of this frontier, and this becomes my new state P. It's going to become what used to be a child state. I'm not going to explore it and expand it, so it's going to become the new parent state for the next iteration of this search. And so after I have visited this, now that I'm going to visit the next iteration, this state, I need to make sure I don't keep visiting always the same state. So I need to make sure that now I'm going to remove it from the frontier. So what I'm going to do is to take the frontier, and I'm going to select from the frontier only the state that starts from position number 2 up to the end of the frontier. And this is going to define my new frontier. So here, if I do that, I select the states that are all the possible states except the very first one. So I start from the second position, third, fourth, etc., until the end of this frontier. And this is what I define as my new frontier. So this line means that I take element number 1 from the frontier and I remove it. So this is where I remove the visited states. So the next state that is going to be visited at the next iteration when I restart this loop here, and when the state P now is going to become the new parent state, I need to make sure I don't keep visiting the same state always. So I'm going to now remove this state P from the frontier. Okay, so what this thing is going to do is that it's going to continue. It's going to, for each parent state, it's going to find its children's, and it's gonna take all those childs and put them in the frontier, and always going to visit next the most ancient element inside this frontier. And it's gonna do that until the parent actually becomes equal to the goal state. And at this point, once the parent states becomes equal to the goal states, this means that I have found a new configuration that is equal to the one that I wanted to reach, which means that I have solved this puzzle, and this is where this loop is going to stop. So if I do this, if I go run this algorithm, so at the end I can output the final state P that is found. So let's see what happens. So I'm going to run this thing, and so here, so it has found state P, and indeed the state P that it has found is the state that we wanted. So 1, 2, 3, 4, 5, 6, 7, 8. So it means that in this case, the algorithm has managed to start from this random initial tile configuration, and it has moved all those tiles in a certain way, in a sequence of action, and it managed to move all those tiles until now those tiles are located exactly where we wanted them to be. The problem with this is that in this implementation of this algorithm, we don't have the memory of what was actually the sequence of action that was found by the algorithm. We have lost the memory of what were the different steps of moving down, moving up, moving left, or moving right the slides in order to reach this stage. So we know that the algorithm has found a solution, but we haven't stored in memory the different steps that were needed in order to reach this position. So we don't have the sequence of the action that needs to be taken. So to do this, we are going to slightly modify this algorithm in order to make sure we keep the memory of all the states that are found. And the other thing that we need to keep as that we need to keep track is every time we find a state, we need to remember what was the parent of this state. So every time you find a new state, a new position for the tiles, you need to make sure you remember like what was the parent, what was the initial position of the tiles before you actually slided them. That way, if we always remember for a given state what was its parents, at the end when we find that the final parent that we find is actually the final state, what we can do is go back and look at what was its parent, and then we can look at the parent of the parent, like the grandfather or the grandmother, and then we can go back generation by generation until we go back to the very initial state. And that way we can reconstruct the entire sequence of actions that was taken in order to convert the initial state into the final states. So for this, what I'm going to do is to keep track of several things. So I'm going to keep track in the frontier. Every time you add something in the frontier, every time you add a state in the frontier, I'm going to keep track of what was the parent ID of the state that I'm adding. So every time I'm adding a new state to the frontier, I want to keep in memory what was the ID of the state of the parent. So I'm going to define an array that is going to store the ID of the parent. So for this, I actually need to define an ID. So I'm going to define an ID I starting from 1, and this ID I is going to be an index that corresponds to all the possible states that I find. Every possible state that I find will have a unique ID, 1, 2, 3, 4, 5, etc. And so this is going to be a unique ID that identify all the states that I find. Okay, and so I will need to keep the memory of those states that I find. So I'm going to memorize the visited states. So for this, in order to keep the memory, so each state is a 3x3 matrix, and I will need to store this for ID 1, 2, 3, 4, 5, etc. So what I'm going to do is to define a three-dimensional tensor or three-dimensional matrix that will be as follows. So I'm going to define this object S, which is going to be three-dimensional with 3 index. The first index will be the ID of the states. So here for I equal 1, it means that for I equal 1, this is going to give me the value of S is going to give me the initial matrix I, the initial configuration. Then for I equal 2, I will get the second state, I equal 3, the first state, etc. And so it's going to be a three-dimensional object where the first dimension is going to refer to the ID of the state. The second dimension and the third dimension are going to be the position X and Y of each style of this state. So here what I'm going to do is that I'm going to take the first parent state that I found. It's initially a 3x3 matrix, and I'm going to put this matrix into S for I equal 1. And then I'm going to do this for all the new states that I found. I'm going to store them into this three-dimensional object S, but I'm going to increment I every time. So that is going to be stored for I equal 1, I equal 2, I equal 3, etc. And I will also make sure that for each state, I keep the memory of what its parent was. For each state I, I'm going to store the memory of its parent. So here I at this point is equal to 1. So this is the very first state, the initial state. So this one doesn't have any parent. So I'm just going to put its 0 as the ID of the parent of this first state, because this state does not have any parent. So then the rest is not going to change much. I'm still going to start the breadth first search. This is going to still continue until the parent state becomes equal to the goal states G. I still will need to find the position of the empty space, so this is not going to change. I will still need to expand this state P, but now the difference is that every time I find a new state, a new child that I'm going to add to the frontier, I will need to save this state, this new state that I have found. So the way I'm going to save this state is that at this point, so I'm going to add it. What I'm doing here is simply to add this state to the frontier. So here I need to save the memory of what was the parent of this state. So here I have found a new child C. I need to make sure I remember that the parent of this child was the ID number I. At this point, we are exploring the state P. State P has an ID I, which is this I here that I will be incrementing. So since I'm adding this new state at the position n+1 in the frontier, I'm going to create a new frontier which is actually have the same format. At the position n+1 of this this frontier, I'm going to say that I'm going to store the ID I. So here I'm going to say that I'm adding C into the n+1 position of the frontier. And for this position n+1, I'm going to store the fact that the parent of this new child C that I have found was, the ID of this parent was I. So I'm going to do this for every child that I found. Here I also found a child and I added it to the frontier. So I'm gonna also keep the memory that this child has the same parent as this child. Like all those 4 childs that I found here, they all have the same parent because they correspond to 4 possible child, 4 possible successors of the parents. Those are the 4 actions that I can take. So each parent can have up to 4 children. So all those 4 children, assuming they exist, they will all have the same parent, the same father or the same mother. Okay, so here I have kept the memory of those. Every time I have something in the frontier, I keep the memory that the parent has an ID number I. So now I need to actually store what are those new states that are visited. So here, this is the position at which I now move to the next state. I was at state number I, that was the parent. Now I'm defining a new parent, which is actually the state that is located at the beginning of the frontier. So it means that now I will move to a new state. So I was at state I, now I'm moving at state I+1. So I will increment I. I'm going to store this this state I in the very same way that I did at the beginning. Here I stored this this state I as being the parent. I'm going to do exactly the same. Now that I have found a new parent, I'm going to increment I, and I'm going to store it to the list of the states. So we have so saved the memory of the new states. I need to make sure I also save the memory of its parent. So the parent was saved here in this list here. So I'm going to in the very same way that I did for the very first state that I had. Here I said that the parent of this very first state was 0 because this state did not have any parent. So I'm going to say that now the new state I that I found, I'm going to say that its parent was actually the parent that I saved in this frontier. So here, since I found P is the first element of the frontier, I'm going to say that I'm going to take in the same way the first element of this frontier and say that this parent information that I stored inside this frontier, I'm going to put it in this to keep the memory that this new state P that I'm now going to explore next, I want to save the fact that its parent was the parent that I saved here. Okay, so now I have in this variable S, I will have the list of all the states that are explored at each iteration of this search, and in this list, in this array S parent, I will have the information of what was the parent of this state that is explored at each iteration of this search. In this case here, since this is an array, I need to use some bracket like this to say that I'm taking this in the same way that I said here that the first element of this array I put it in as state P. I need to say that the first element within brackets like this of this frontier, I put it as I save it as the first element of this of this variable here. Here, like the reason that in some cases we are using some brackets like this or like this is because those are two different types of Matlab objects. One is an array. An array is just going to be a list of different elements one after the other, while when I define S like this with this kind of brackets, this is actually a matrix where you have one element at position 1, 2, 3, 4, 5, etc. So this is a matrix, while this is an array. The difference here is that this array, each element of this array is actually, in this case, each element of this array is a matrix itself, while in the case of a matrix, each element of a matrix is a real number or an integer number. In this case, this is an array, a list of different matrices. So this is a collection of different matrices, a collection of the different states. So in this case, for this kind of array, you need to use this kind of bracket. Okay, so the last thing that I need to do is that since I am now at this step here, I am removing from the frontier the first element of this frontier. Since this first element becomes now the new parent state, I also need to make sure that I'm going to remove accordingly the element from this frontier here to make sure I remove the parent information of this element that I'm removing from the frontier. So I'm going to take the frontier f parent, and same thing, I'm gonna select only the element 2 to n. So I'm going to exclude the element 1. So I'm going to select all the elements 2 up to the end of the frontier and save it into the frontier, which is going to effectively remove the first element of this frontier. Okay, so if I do this, what it's going to do is that it's going to save all the states that are visited one after the other in the variable s, and it's going to store for each state what was the parent of this state. So that doesn't still mean that I have found the most optimal sequence of action, because if I take the breadth first search algorithm, it's going to explore a lot of states, but that doesn't necessarily mean that those states are the one that corresponds to the most optimal sequence of action, because the breadth first search algorithm is always going to explore all the very first states that it finds. So it goes generation of states by generation. It always focuses on the oldest generation of states, step by step, generation by generation. So it always explores all the possibilities of all the states that can be reached by all the possible actions. So most of those states are actually not good actions to take. Like, for example, if you start from an initial state, there is only one action that is going to be the most promising one, but actually this algorithm can potentially find 4 possible actions depending on where the void is, but out of those 4 actions only one is the good one. So we need to make sure that out of all those states that were found by the search algorithm, we only isolate the ones that correspond to the path that eventually led to the goal G, that the configuration that we wanted to find. So here what we are going to do is to, based on this information of the states and of their parents, I'm going to recreate the optimal path. So I'm going to recreate the optimal path, where the path is the optimal sequence of actions that led to the goal state. Okay, so let's do that. So that's a pretty easy steps because we did all the hard work here. We saved all the information. So now what I'm going to do is I'm going to go back in time. We know that at some point when this algorithm stops, it will stop because the state P, the parent state, becomes equal to the goal state. So this is when the algorithm stops. So we know that when it stops, P is equal to the goal. So if we want to recreate the optimal sequence of action, we need to find what was the parent of P, what was the state that was the parent of P, the state for which we started. We moved one tile, and by moving this tile we actually reached the goal. So that was the parent of P. So we need to go back and find what was this parent of P, and then we need to look at this state, this parent, what was its own parent, and what was the parent of the parent, etc. So we need to go back in time, and at each parent we need to find what was its parent and go back until we go back to the very initial state. And the reason we need to go back in time is because it's very easy to do this. Why? Because if you take a given parent, each parent can have several children. Each parent can have up to 4 children, which corresponds to the 4 possible moves that you can take. So this is hard to find what is the optimal sequence of action because each parent can have between 2 to 4 children. But going the other way around is very easy because each child has only one parent. So it's in this case there is no ambiguity. Each child has only one parent, so we can directly go back in time and find the optimal sequence of actions. Okay, so I'm going to start by doing some initialization. So here what I want to find is the sequence of all the actions, all the states that I need to explore. What is the optimal sequence of the states that I need to explore to go from this initial state up to the goal state G? And I'm going to say that I'm going to store this in the state P. So P is going to be the initial parent state that we are going to start. And in this case, what we are going to do again is to start from the very latest state that was found by this algorithm, which is the goal state. And I'm going to go back in time, determine what was its parent, and look at the parent of the parent of the parent of the parent, etc. So let's start by saying that the initial state that we stopped the previous algorithm at was actually the last state that was stored in this variable s. So this algorithm stopped at a given position I, where I was the ID of the latest state that was explored, which turned out to be the goal state, and that's why this algorithm stopped, because P became equal to the goal G. So I'm going to restart from there. So I'm starting from the latest state that was found. So this is I'm restarting from the final state, which was the goal. So I'm restarting from the goal here. I'm doing exactly the opposite of what I'm doing in this search algorithm. Here I'm starting from the initial state and I want to find the goal. Now I'm going to do the exact opposite. I'm going to start from the goal and I want to go back to the initial state. That's how I'm going to find the optimal sequence of action. Okay, so I want to store all the states that I need to explore in order to go from the initial to the final state, or in this case here from the final to the initial. So for this I'm going to define an integer which is going to be the ID of the parent. So for example, here I start from the initial state, which is actually the goal state, and I want to find what was the parent of this state. So the parent, I stored it inside this variable here. Here, this variable tells me the parent of the state I. The state I is the final state that was found in the previous search. So state I is the goal. And here, this variable is going to tell me what is the parent, the ID of the parent of the goal state. So that was the last step, the previous state that was explored and expanded before I eventually found the goal. So this is the ID of the parent, IDP. This is the ID of the parent. And what I want to find is the path. The path is going to be the sequence of all the actions, or the sequence of all the states that are going to be explored. And this path, I'm going to store it into an array, which is going to be an array that is made of all the states that need to be explored from the initial to the final. So here I'm going back in time. So I'm going to start from the final state. So P is the corresponding to the final state, so the goal state. So that's going to be the beginning of the path, and I'm going to go back in time from this. So for this, I'm going to do a loop now to loop on the finding the parent of this state, and then finding the parent of the parent, and then the parent of the parent of the parent, until I find the initial state. So this loop is going to continue. I'm going to find the parent of each state until I find that the state P, the parent that I will find, becomes equal to the initial state. So now this loop is going to be exactly the opposite of this one. Here I was doing this loop until the parent state becomes equal to the goal. Now I'm going to do this loop until the parent state become equal to the initial states. So I want this loop to continue as long as the state P is not equal to the initial state I. So if state P is not equal to state I, then it means that this state P is not the initial state, so I need to find its parent. So to go back in time, I need to find the parent of this state P. So for this, I'm going to do exactly the same thing as this. I'm going to find the parent of the state P. In this case, this state P, its ID, the first parent of the final state, was this IDP. So in this case, we start from state P. So this state P, I find its parent. This is the state IDP. So now I need to look this new state P that I have found. Is state P the initial goal or not? So it's not. So I need to find its parent. So I'm gonna take this state IDP. This is the parent of P, and I'm going to find the ID of the parent. So this is gonna give me the parent of the state of the parent of P, and it's gonna give me the grandparent of P. So I'm gonna go back one generation, and I'm gonna say that state P now is gonna become the new parent. The parent of state P is gonna become the new parent. So I'm gonna say that the state, the former parent of P, which was the state number IDP, I'm going to make this new state become the parent. So here what I'm doing again is I start from state P. I look at what was the parent of this state. So that gives me its ID, the ID of the parent. Now I look at this new state IDP, and I want to know its parent. So I look at the parent of this parent, which is now the grandparent of the initial state P here, and I look at what was the configuration of this grandparent, and I store it as P, so that the grandparent now becomes the next parent that I want to explore. And so this is a new state. I'm going to save it in the path. I'm going to now expand the path. I'm going to say that I'm going to append this state to the path in the same way that I was appending the frontier. So now I'm saying that this state P, I'm adding it to the path. Okay, so here what it does, it's gonna look at the parent of the parent of the parent of the parent until the parent actually become the initial state. And once this is the case, this loop is going to stop, and then it means that I will have found the path that corresponds to all the states that have been explored during this optimal sequence of action. I will have started from the final state. I found the parent of this state, then I found the parent of the parent, then the parent of the parent of the parent, until I go back enough generations to find the initial states. And now I have a path that corresponds to all the states, except that this path now is organized in the reverse way. I start by the final goal, then I added the parent of this goal, then the grandfather of this goal, then the grandfather. So I'm going back in time. So if I want to recreate the path starting from initial to final, what I'm going to do is to flip the path. I'm going to reverse. I'm going to use the flip command to reverse the path. The only thing that this is going to do is just to completely switch, to do a symmetry of the path, so that here, since I'm going back in time, the parent, I find the parent, then the parent of the parent, then the parent of the parent of the parent, etc. I'm going to flip this path in order to change it into now a sequence of states that starts from the initial up to the final states, because this path here that was created was doing exactly the opposite. It was starting with the final and then was gradually coming back towards the initial. So I'm going to flip it, and now this path is going to give me the initial, then the second state, then the third state, until it reach the final states. And then I'm just going to print what was this path, what was the sequence of all the actions that were taken. Okay, so I did a typo here, because f parent is also an array, so I need to use this kind of bracket, and I need to do that for all those 4 actions. Sorry about this. Okay, so let's see if this runs now. Okay, so I think that looks good. Okay, so let's see what it has found. So here, again, so as a reminder, we started from this state I, which goes with the tiles being located as follow, with 4, 1, 2 as the top tiles. So this is indeed where we start from this when we recreate the optimal path. Here we define the path with all the states. We flipped the path so that we identify the sequence of all the states starting from the initial to the final one, and so we expect that this path is indeed going to give us the most optimal sequence of actions to go from the initial to the final states. And here those matrix is going to correspond to the different states to go from the initial to the final. So let's just make sure. So the initial was 412753086, where 0 is the empty space. So indeed the initial one is this, so 412753086. and eventually the goal state was 1, 2, 3, 4, 5, 6, 7, 7, 8. And so indeed, this is the final state that we find in the path, like the one we wanted, where the tiles are ordered as 1, 2, 3, 4, 5, 6, 7, 7, 8. So now let's just check that this path makes sense to make sure that our algorithm is working well. So let's understand what the computer has done. So we start from this configuration. So here what the computer has done is that it has taken the tile 7 and it has moved it down. Okay, so everything else is fixed, but just 7 was moved down, which means that 0, the empty space, is now located at the second line, the second row, first column. So starting from this, what it has done next is to move the tile number 4 down. So now the 0 is now located at the top. Then it took tile number 1 and moved it left, so that now tile number 1 is located here. Okay, so here we can see that there is an issue with the algorithm, because here, so we can see that going from this to this, so it has moved tile 2 towards the left, which is fine, but here we are missing one state here. We need to go from here to here. We need to move the tile number 3 up, but we also need to move the tile number 6 up, which means that this is a good reason to actually visualize what the algorithm is doing to find out the possible problem. And here, the reason that we are missing this is that we are directly switching from the final state to directly its grandfather. We are missing the father of the final state. Here, this is the final state. We are missing the father, which would be to simply move 6 down. Here we have directly the grandfather, where not only 6 has moved down, but also 3 has moved down. So this is because we are, in this case, we are directly switching from the final state to its grandfather rather than its father. So let's check carefully the recreation of the optimal path. So we start here from the final state. So P, this is the final state. So this is good. This is the last step that we have here. This is indeed the final state. What I want is to find what was the father of this. So this is where I did a mistake. Here, the parent of P, this is where it's the parent of P is going to be found in this line. And here, IDP is already the parent of state P. So if I take the parent of IDP, this is going to be the parent of state P. So this new state P is actually going to be the grandfather of state P. So what I need to do to fix this is to say that I'm going to say initially that I'm going to initiate this variable IDP as being equal to I, where I is simply the ID of the final goal state. Here, at this line, I'm going to find the parent of the goal state and store its ID as the integer IDP. And then I'm going to say that the state corresponding to IDP is going to become the new parent. So now this is now going to be the parent of the goal state rather than the grandparent of the goal state. So let's see if that helps. I'm going to rerun this part. So now we have one additional step. We used to have only 6 states. Now we have 7 states. So this is a good sign. So let's just check again to make sure everything is fine. So we start from the initial. We move 7 down. We move 4 down. We move 1 left. We move 2 left. We move 3 up. And then we move 6 up. And now we have found the final goal states, which means that in this case, so now, so the problem has been fixed, and now we have found the optimal sequence of actions that you can use to go from the initial state to the final states. So what this analysis tells us is that first, if I want to go from the initial state to the final state, the shortest path that I can find in order to do this are those 1, 2, 3, 4, 5, 6 steps. Here, because of the breadth first algorithm is guaranteed to give us the most optimal sequence of actions, we know that there is no other fastest way to transform these initial states into the final states. There is no other shorter path in order to reach the solution. This algorithm is guaranteed to give us the shortest sequence of action. So we know that the fastest that we can solve this puzzle is by taking those 6 actions. Maybe there is some other path. It's possible that there is an other path with 6 actions or more, but we know for sure that there is nothing shorter than those 6 actions. And by using this, we can recreate what was the actions that was taken by the algorithm. But if we look at here, like the variable s, the variable s corresponds to all the states that were explored by the algorithm. We saw that to find those 6 actions, the algorithm actually explored and expanded 245 states. So the algorithm here, you can see that it's very inefficient because it explored a lot of states, like it explored 245 states before it could find this optimal sequence of actions. So the advantage of the breadth first algorithm is that it's guaranteed to give you the most optimal sequence of actions, but as you can see here, it's not very efficient because it's exploring and expanding a lot of states. And so the problem with that is that not only you waste some time exploring some states that are not very useful, but also you end up with a need for a large memory because you need to keep the memory of all those states that you are exploring, and this can take a lot of memory on your computer because you need to keep the memory of all those states, even though most of those states actually are going to be useless. Here we realize that we can go from step 1 to the goal state with only 6 moves, but still we had to keep the memory of 245 states. So most of those states are actually useless. And also the disadvantage of this search is that it's uninformed. So we are just making some random moves, and this algorithm is not aware of whether those moves are actually looking to be promising or not. So if we wanted to make this algorithm a little bit smarter, there would be different way to make this algorithm faster and smarter. The first thing is that here I'm just checking all the 4 possible moves that I can take based on where the void is located, which means that it's possible that, for example, if I move one tile to the right, at the next step, I could be very well taking the same tile again, and this time moving it back to the left and going back to the previous states, which would be completely useless because I would be coming back to the previous state. But in this algorithm, there is nothing that prevents this. So here what I would need to do is every time I find a new child, I would need to check if actually this child has not been already visited, or maybe it's already in the list of the visited states, or maybe it's somewhere in the frontier already. But here I'm not doing this. So one way to make this algorithm more efficient would be to check every time you find a new child, has it already been explored yet? If it has been explored, then it's not worth coming back to this previous configuration because we already expanded this configuration. So that is one obvious improvement that would deserve to be made. And the other thing is that it would probably be more efficient to use an informed search algorithm rather than an uninformed search algorithm. So here, for example, you could use either an A-star algorithm or a greedy algorithm. this would require you to define a distance. And here, for example, the kind of distance that you could define is to look at the values, at the position of the tiles, and look at how far are, at a given state, how far are the tiles from the position you want them to have in the goal states. And by looking at how far those tiles are from the final position that you want to reach, you could define a distance and use this distance to implement a greedy algorithm, a greedy search algorithm, or an A star search algorithm, which would probably be a much more efficient algorithm, because it would be more likely to go towards the right direction, the most promising direction, which brings the tiles closer to the position where they need to be, rather than doing some random moves that are not guaranteed to go towards the most promising state. So nevertheless, so those different steps is still an illustration of what it would take in practice to implement a search algorithm. So again, the different key steps are always going to be to define a frontier, and then to start exploring and expanding the different states. And so every time you expand a parent state, you need to store its children using this the frontier. And then the core of the search algorithm is to decide within the frontier which is the next state that you are going to visit. So in the breadth first, you always visit the most the oldest state, the most ancient state. In a depth first search, you would always be favoring the new states that have been found. Here, that would be very inefficient to use a depth first algorithm for this problem, because the depth first algorithm is not guaranteed to find the solution in this case. You could very well continue in one direction, and in this case there is no dead end in this game. Like every time you move a tile, you can move this tile up to its initial position, so there is no dead end. You are never blocked in this game. You can always move something. So a depth first algorithm would not be a good choice, because you could continue forever moving those tiles away without finding the goal. So it's, in this case, if you have to choose between depth first or breadth first, it's probably a better idea to use the breadth first. But for example, if you were using a greedy algorithm where you would favor the states that have a distance that is as small as possible to the goal states, you would need to look at the different element that you have in your frontier, and rather than just choosing the first one, you would choose the element that has the closest distance to the goal states. You would look at, within this frontier, within all the states that you have found, which one is the one that looks the most similar to the goal states. So in the different states that you have in your frontier, in which of those states the tiles appear to be located the closest to the goal state, and that's the next state that you would take and start exploring, rather than just taking the first element of the frontier. So this kind of greedy, informed algorithm would likely to be more efficient to solve this game. But in this case, the breadth first algorithm is poorly efficient, but it's still gonna work at some point if you are patient enough. So that's it for this tutorial. So this is meant to be an example for your first homework. So in your first homework, you will need to implement this kind of search algorithm to solve some other types of logic problems, to explore a given problem and explore to find the most optimal sequence of action to solve a logic problem. So thank you for watching this tutorial.